So the last part that we're going to talk about today are the biological functions of polysaccharides. So we left off talking about how the anomeric bond between the carbonyl and an alcohol is called a glycosidic bond. And if I have a glycoside, that's an example of a polysaccharide that's formed between two sugars. And we talked about how the configuration about the anomeric carbon is actually locked in a glycoside. So that means that mutarotation is no longer possible. I can obviously break down a disaccharide by using hydrolysis, so using acid and then water to add back in. And we talked about the most common reducing sugars, for example, the linkage between two anomeric carbons. And we kind of left off talking about homopolysaccharides and heteropolysaccharides. So if we take a look at glycogen, it's our first example of a branched homopolysaccharide of glucose. Its monomers form alpha-1,4 linkage, where you have branch points with alpha-1,6 linkers every 8 to 12 residues. This molecular weight can reach sometimes several millions, and it's the main storage polysaccharide in animals. If we contrast that with starch, starch is a mixture of two homopolysaccharides of glucose. So amylose is an unbranched polymer of alpha-1,4 link residues. Amylopectin is actually branched like glycogen, but the branch points with alpha-1,6 linkers occur every 24 to 30 residues. The molecular weight of amylopectin is probably up to about 200 million, excuse me. And starch is the main storage polysaccharide that we actually see in plants. Notice, right, there's this common motif of repeating disaccharide units. And so when we're thinking about these molecules, it's useful for us to think about what they actually look like. So here's an example of amylose. And that's going to show you both the non-reducing end as well as the reducing end of the sugar. And it's useful to be able to think about where the main chain would be as opposed to where I would see branch points. This gives you an example of the mixtures of amylose and amylopectin and starch, both in terms of the non-reducing ends as well as the reducing ends. And it shows you a little bit like what those branching points would look like. If we think about glycogen and starch, these are often stored in granules in cells. So granules contain enzymes that actually synthesize and break down these polymers. Glycogen and amylopectin have only one reducing end, but many non-reducing ends. And so these enzymatic processes occur simultaneously at many of the non-reducing ends. If I compare that with cellulose, cellulose is a branched homopolysaccharide of glucose. It's got monomers that form beta-1,4 link chains. The hydrogen bonds form between adjacent monomers, and then I have additional hydrogen bonding that exists between the chains. That structure is very tough and water insoluble. It's actually the most abundant polysaccharide that we see in nature. So for example, cotton is nearly pure fibrous cellulose. And if you take a look at the hydrogen bonding that exists in cellulose, right, there are a lot of options simply because there are a lot of hydroxyl groups. So there's a lot more stability that can exist because of hydrogen bonding. If we think about cellulose metabolism, it's the fibrous structure and the water insolubility that makes cellulose a very difficult substrate to act on. Fungi, bacteria, and protozoa all secrete cellulase, which is an enzyme that allows them to use wood as a source of glucose. Most animals, though, cannot use cellulose as a fuel source because they lack this enzyme to hydrolyze the beta-1,4 linkages. Only ruminants, so for example, a cow or termites, live symbiotically with microorganisms that can produce cellulase. And it's really a unique enzyme in that it has this ability to help in the fermentation of biomass to help create biofuels. Chitin is another example of a homopolysaccharide that we're going to take a look at. It's comprised of N-acetylglucosamine. N-acetylglucosamine monomers form beta-1,4 link chains. These forms extended fibers are very similar to cellulose. Chitin is hard, insoluble, and it cannot be digested by vertebrates. It's a tough structure, but it's flexible and it tends to be fairly water insoluble. So we find it in the cell walls in mushrooms, in the exoskeletons of insects and spiders and crabs and other arthropods. This is an example of what the N-acetylglucosamine looks like. And then we're going to finish up by talking about agar and agarose. So agar is a complex mixture of heteropolysaccharides that contain modified galactose units. So agar serves as the component of the cell wall in some seaweeds. Agarose is one component of agar. And the agar solutions form gels that are commonly used in the laboratory as a surface for growing bacteria. So agarose solutions form gels that can also be used for the separation of DNA by electrophoresis. Here's an example of what agarose looks like. You can see the repeating units. And then glycosaminoglycans are linear polymers of repeating disaccharide units. So one is typically N-acetylglucosamine or N-acetylgalactosamine. So they're typically negatively charged either because of the uronic acids at the C6 oxidation or because of sulfate esters. And they are extended hydrated molecules, so this tends to minimize charge repulsion, and they form this beautiful meshwork with fibrous proteins, making up extracellular matrices. So we see these in connective tissues or in the lubrication of joints. And you can see the glycosaminoglycan here, where you have the repeating disaccharides. So hyaluronate and chondroitin are two great examples. So you can actually see the linkage between those two here, and actually also see the functionalization. And you can see the number of disaccharides per chain, say for example in keratin sulfate or in heparin. So heparin and heparin sulfate are linear polymers, where heparin sulfate is a heparin-like polysaccharide, but it's actually attached to proteins. These molecules have the highest negative charge density of biomolecules that we know to date. They actually prevent blood clotting by activating protease inhibitor antithrombin. And the binding to various cells regulates the development and formation of blood vessels. They can also bind to viruses and bacteria and decrease their virulence. So these are just a few of the examples of the biological function of polysaccharides. Thanks again. Have a great day.